So for this data set, how do you find the mean? So yes, we add them all up and divide by what? 5, because there's 5 of them. If we add them all up, what do you get?
30. Oh, no.
Let's see there, 51, 81, 112, 150, divided by 5 is 30. To find the median, what do we do? There's 2 steps.
5 divided by 2.
What's that?
5 divided by 2.
Okay, it's 5 times 1/2, you got it, which is 2.5. What does that tell us? Well, since it is a decimal, you round up, so it's the 3rd number in the list. And I did put these in order, so that's the 3rd number is 30. So the median is also 30. I didn't ask for a mode because in this small set,
How do you find the mode again?
mode is just the number that occurs the most often. No numbers repeated there, so there's really no mode. How do we find the range?
Smallest number plus biggest number divided by 2.
Smallest, careful, you're thinking mid-range.
Yeah.
Mid-range would be smallest plus biggest divided by 2.
What's just range?
Just the range is the largest minus the smallest. This has a range of 15.
Just smallest minus largest?
Largest minus smallest. Yep. And finally, standard deviation. This is what we ended on last class. Well, yeah. The first step is to find the mean, which we've already found. So step 1, the mean equals 30. We've got that. Step 2, we're going to have to list out our numbers. So 23, 28, 30. 31, 38. Very good. And we are going to subtract the mean from each. So 23 minus 30 is -7. 28 minus 30, -2. 30 minus 30 is 0. 31 minus 30 is 1. And 38 minus 30 is 8. What is the next step? Square them all, yes. Step 3 is squared. So, -7 squared is 49. -2 squared, 4. 0 squared, 0. 1 squared, 1. And 8 squared, 64. Step 4. What's step 4? Find the sum, add them up. So I add those together and I've got what, 118? I believe. Step 5. So divide by n minus 1. What's n? Yep, so for this case, n is 5, right? So 5 minus 1 equals 4. So you divide by 4. What is that, 29.5? That number, by the way, would be called the variance. 29.5 after you've divided by n minus 1. What is then step 6? Square root the variance. So this is going to give us about 5.43. That is the standard deviation.
What does that number represent?
What that number represents is on average how far each point is away from the mean. You know, this one is 7 units from the mean, 2 units, 1 unit, 8 units. That averages out to somewhere around 5.43. Yeah, well, yeah, it's the old term for standard deviation is the RMS deviation, the root of the mean of the square deviations. If you actually follow through, you can actually see it. It is the root of the mean, you add them up and divide, of the squared deviations. Okay, so the big question is, what do we use this stuff for? So, the biggest application we're going to look at, remember we looked at that distribution yesterday with the bell curve. And we talked about how the mean, median, and mode, if it is a good normal distribution, should all be the same number. Now, they may or may not be, depending on how they're scattered. In this case, the mean and the median, at least, are the same number. So that's indicating that there's a good chance that this is a symmetrical curve like this. If the mean and median are slightly different, that's telling us that the curve isn't perfectly symmetrical. If they're very different, it's telling us it's nowhere near symmetrical. But on a symmetrical bell curve like this, that mean and median should be the same. So we mentioned yesterday the median is actually a better measure of center. But because of efficiency, if we have a large set of data, putting them in order and finding the middle is kind of tedious. So finding the median can be tough. And also for a mean, we can keep a running mean. Every time we add a new number into the list, we can change the mean really quickly. The median's a little trickier. You've got to rearrange the order every time you put a new number in. So in manufacturing, we tend to use the mean instead of the median. But like I said, on a good set of data, they should be the same number or really, really close to the same. So one thing that we use that mean along with the standard deviation for is something called the empirical rule. The empirical rule goes off of this bell curve thingy again. Now I made this one a little wider just so I had room. At the very center is the mean, or the median, but we're going to use the mean. If we go up in steps to the left, getting smaller, we go down by a standard deviation. So this is -1 standard deviation. This is -2 standard deviations, and this is -3 standard deviations. And then we go up in steps of a standard deviation at a time. So this is +1 standard deviation, and I'll put numbers in here in a minute to make it a little clearer. +2 standard deviations, +3 standard deviations. The numbers that are going to go on bottom here will change depending on the mean and standard deviation of the data we're looking at. The numbers that I'm about to put up here inside the bell curve will not change. 34% of the data should be between the mean and 1 standard deviation below the mean. 34% should be between the mean and 1 standard deviation above the mean. Between 1 and 2 standard deviations on each side should be 13.5% of the data. Between 2 and 3 standard deviations should be 2.35% of the data. And then outside of 3 standard deviations should be 0.15% of the data on each side. As I said, those percents will never change. What changes are the numbers along the bottom of the curve. Let me show you what I mean by that. Let's say you guys get done school and you find a good job, and you need to move, and you're looking at buying a house. So you want to price out houses. And what you're looking for is a 3-bedroom, 2-bathroom house. 3-bedroom, 2-bath. And you do your research. And in the area that you're looking, you decide that there have been no major fluctuations in the market for about 3 or 4 years, which is important because there's a big price spike like there was back in 2005, 2006. Prices were just climbing out of control, or a huge price drop like there was in 2008, 2009, when prices just, some houses lost 30% of their value overnight because the market just fell out. If any of those have occurred, you have to account for it because that changes things. But you've done your research, and none of those things have happened in the last 3 or 4 years. So you're going to look at all the 3-bedroom, 2-bathroom houses that have sold in this area over that period of time. You find that the mean price is $140,000 with a standard deviation of $40,000. Actually, more realistic. Let's go with $30,000 for that. Be a little bit more realistic. So what does that mean? Well, that means I can come to this curve now and I can fill in the numbers on the bottom here. What is the mean? Well, 140,000 is what goes in the center. The standard deviation is 30,000. So this number here is going to be the mean minus 1 standard deviation. So 140,000 minus 30,000, giving me 110,000 there. So I'm going to pause. Any questions on where that 110,000 came from? The 30,000, I just had to give you that. Yeah, the mean and the standard deviation, I had to give you those numbers. So the 140,000, we subtracted the standard deviation of 30,000 to get 110. Now to go to the next step down, we subtract the standard deviation again. So what's this going to be? 110 minus 30 is going to be 80,000. Then the next step, we're going to subtract it again. This is going to give us 50,000. 80 minus another 30 is 50,000. Going to the right, we're adding the standard deviation. So 140 plus 30, 170,000. Again, 170 plus another 30 is 200,000. And plus another 30 is 230,000. So let's say you find a house that you just absolutely love. Has everything you want, plus a lot of extra little things that are really kind of cool. It is priced at $200,000. Your realtor is telling you you need to put in an offer on this house right now because it's not going to be around for long. It's going to sell real quick. You better put in an offer before it's gone. Well, what this all tells us, $200,000 is right here. Looking at less than is this left side here that I just circled. If I add up all of those percents, that comes up to 97.5%. What that's telling you is that out of all the houses in that area with 3 bedrooms and 2 baths that have sold in that period of time, 97.5% of them have been cheaper than $200,000. So what's that telling you about the chances of you finding a house cheaper than $200,000 that you still like? There's probably a pretty good chance, right? You don't need to be a top 3% house, right? In fact, this tells us a lot. If I wanted to know what percent of the houses that had sold, what we expect to be, what percent we expect to be between, let's say, 80,000 and 170,000. Well, here's 80,000. Here's 170,000. We add those up. That adds up to, let's say, 81.5%. We expect 81.5% of houses to be in that price range. Does that make sense? So let's say you're looking at a job and you're offered, well, let's say you do some research in the area and you find that mean starting pay for the position that you're hired for is $14.30 an hour. And the standard deviation in the starting pay is $1.70 per hour. We're going to come back and talk about what you were offered in a minute. But I want you guys to find what percent would you expect to be between $12.60 an hour and $16 an hour. That's a standard chart. All that should ever change are these numbers down here. The percents up here will always be the same. So I give you a minute to copy those down?
Yeah.
Yep. So now we'll scroll back down here. There's the information given. I'm going to leave the percent sign off here because I made these a little bit smaller. What numbers go along the bottom in this? Easiest to start in the middle. What's going to go in the middle? 1430. Then what goes here? 1260 here. 1090 and 920. Here, 16, then 1770 and 1940. So you have 1260 and 16 is right there. I add those up. That is 68%. You had the 34 and the 34. Because they're between the 1260 and the 16. What percent would you expect to be less than 1090? But here's 1090. Less than would be those. That adds up to 3.5. Nope, the 13.5 is on the outside of it. So it's just the 0.15 and the 2.35. More than $16. Here's 16. What percent do those add up to? 16%, yes. So I said, those percents in the curve never change. All that changes are the numbers down here based on what your mean and standard deviation are. What's that? Less than 1090? Here's 1090, right? So less than would be those. So you got the 0.15 and the 2.35 add up to 2.5%. Well, that works well for numbers within a population. But what if you have to compare two things that are from different populations? We use something called a Z-score. What Z-scores do is they standardize things. They standardize values from different populations. For example, all of you had to do some sort of testing before you came in here. So let's take a look, and I realize you guys took an Accuplacer or a TABE test to get in here. But let's say you took the ACT and the SAT, your standard college placement exams, or college entrance exams. And let's say you're going to evaluate somebody who took these tests, and you're going to compare two people. One person comes to you, scored a 32 on the ACT. Another person comes to you and scored a 1650 on the SAT. And you want to know which is a more impressive score. They're both pretty good, by the way. Well, to know, we're going to use a Z-score. What a Z-score is, the Z-score is the number minus the mean for its population divided by the standard deviation for its population. So let's say that for all people who took the ACT, the mean score is 18. And let's say the standard deviation is 5. Let's say for the SAT, for all people that took the SAT, the mean score is 1,050. And the standard deviation is 250. So now we calculate a Z-score for each. The Z-score for this one is going to be its value of 32 minus the mean for that data set of 18 divided by the standard deviation for that data set, which is 5. Well, 32 minus 18 is 14. 14 divided by 5 is 2.8. What that is telling us is that score of 32 is 2.8 standard deviations above the mean for all students, all people who took the ACT. Now let's go to the SAT score. This person scored a 1650. We're going to subtract the mean of 1050 and divide by the standard deviation of 250. 650 minus 1050 is 600. Divided by 250 is 2.4. That person's score is 2.4 standard deviations above the mean. So this one is the more impressive score. It's more standard deviations above the mean for its population. Because each of those populations will take on this same bell curve. 2.4 standard deviations is somewhere in here. 2.8. What if you're saying that more smart people took one test than the other?
Yeah.
Well, to make that work, you have to have large enough populations for each that it equals out. I mean, if you only had like 150 people that took each test, it's not going to work. But there are literally tens of thousands of people who take those tests each year. So it equals out that, there's still that very slight random chance. And if you get into your higher level statistics, that's actually what most of what they're coming down to is how do you account for that random chance that if, like when we're doing a sample of parts and we want to make sure that it's at least a certain weight, it has to be this weight or a little bit above. And we take a sample and the mean of that sample is slightly below that weight. Does that mean all of our parts are being produced below weight? Not necessarily. It means we may have just accidentally taken a sample that had a bunch of really small parts in it. So how do you account for that? How do you eliminate that chance or reduce that chance at least? We will talk more about the empirical rule and Z-scores tomorrow. I have a worksheet I'm going to give you today that deals with this, and there's something called a run chart on the end of it. We'll talk about that tomorrow as well.